Okay, welcome back everyone. So for the last lecture of the day, we're going to talk about how to control for or adjust for sample structures such as population structure, as well as relatedness among individuals in a genome-wide association study. Okay, so genome-wide association studies to date have included hundreds of thousands of individuals for mapping of both dichotomous and quantitative traits. So large-scale genomic studies often have very high dimensions, many more SNPs than individuals, so tens of thousands of individuals and millions of genotype SNPs, as well as like a variety of trait values. Okay, so the vast majority of these studies have been conducted in European populations, but as I mentioned, recent studies have investigated more diverse populations, and so non-European populations have largely been underrepresented, but we are seeing a lot more genetic studies with diverse ancestral populations. Okay. So the observations in associations can be confounded by population structure. I mentioned one example of that for example, in the Finland slide from the previous lecture. So population structure is just the presence of subgroups in the population with ancestry differences, and we talked about approaches that are available for identifying population structure. And principal components analysis is by far the most used approach to identify population structure. So if you do have samples with population structure, if you fail to account for it, you could have false positives or spurious association. So that's always a concern in genetic association studies. Are your results due to you finding a SNP or a genetic region that's truly associated with it, or is it somehow explaining something else such as ancestry? Okay. So in statistics, a confounding variable is an extraneous variable in a statistical model that correlates with both the dependent variable and the independent variable. Okay, so what we want is the relationship. We want to know, does genotype associate or influence our trait? But we can be concerned of, let's say you have a trait that's associated with ancestry, and your genetic marker is also associated with ancestry. So you can see an association through trait, but it's just telling us about ancestry. It's not a direct association with the trait of interest. Okay? So it's a serious concern. Ancestry is confounded in genetic association studies. Particularly if you have a trait associated with ancestry, and you have genotype associated with ancestry, but the genotype is not directly associated with your trait. So that's something to be concerned about. And so we essentially want to control for ancestry. After adjusting for ancestry, do we see a relationship between genotype and trait? Okay. So why is this a concern? Because ethnic groups and subgroups often have or definitely share distinct dietary habits and other lifestyle characteristics that leads many traits of interest to be correlated with ancestry. Okay? So a lot of traits of interest have a strong environmental component. Most complex traits of interest often have more environmental components that are influencing the trait than genetics. Not that genetics is important, but the environment plays a huge role. If you have ethnic groups or subgroups that share similar environment is everything that's not genetic. Okay? It could be diet, exercise, where you live, stress, and that influences your outcome, then you can have a major problem with confounding in genetic association studies, so you want to control for that. So what about spurious association in the case control design? So let's say we have a trait of interest where either you have the disease or you don't. Okay. So at its most basic, case control association testing is just essentially comparing allele frequencies in the case and the control. At this marker, are cases more likely to have the type A allele than the controls? So if you think of case control studies, that's essentially what it is. Are controls or cases more likely or less likely to have a particular variant? If they are, then we have an association. So in this example here, we have population 1, okay, is in red, and then dark circles are the cases, and open circles are, filled circles are the cases, and open circles are the controls. And population 1, population 2, same thing, dark circles are the cases, and open circles are the controls. In this study here, we sampled more cases from population 1 than from population 2. So red population is overrepresented among the cases. So any genetic markers that are not influencing the disease are not involved in case control status, but there are differences in the frequency between the cases and controls, and different in the frequency between the populations. Let me start over again. Any genetic marker that's not involved with the disease, but there are significant differences in the frequencies of population in population 1 and population 2, you're going to get an association because population 1 is overrepresented in the cases. So any genetic marker where there's a difference in the low frequency between the population 1 and population 2, you're going to get a signal because population 1 also has more cases in our sampling. So that's a serious concern. So you're going to get a whole bunch of spurious association. For example, if you have a poorly designed study where you don't, or analysis where you don't account for the fact that population 1 is overrepresented in the cases. So any marker where there's differences in the low frequencies between population 1 and population 2, you're going to show a signal between differences between case and control. Just because population 1 is more likely to be a case in our sample. Does that make sense? Okay, so that's a serious concern. Same is true for quantitative trait association testing. If you have a population that has higher values, trait values on average, than another population, then any markers where there's a little frequency differences between the population, you're going to find an association. So it's spurious association between the trait and genetic marker. If one population is overrepresented. So if you have individuals from population 1, and they're more likely to have the extreme phenotype and they're overrepresented, then you're going to find an association at any marker where there's differences in the low frequencies between these two populations. So how do we control for it? So let's suppose we have data and we have a phenotype of interest, Y. Here, Y is quantitative, but if it's dichotomous, we would just think of it, Y can be 0, 1. Okay. And we have a genotype data at a SNP of interest, where here we're just coding it as additive, an additive model, 0, 1, and 2 copies of a reference allele. Okay, so this is the genotype vector for all of our individuals in our sample at SNP-S. Okay. So genomic control was one of the first approaches proposed to control for population structure. So Devlin and Catherine Rader, they came up with this approach. So what they do is they first do an association study without doing any correction. Okay? So they do a regular association study, don't do any correction. For example, the Armitage's trend test statistic, okay, or Pearson chi-square statistic. You just do an association study without doing any correction. If there is no population structure, okay, then the vast majority of these SNPs are not going to be associations, so we're under the null. This should follow a chi-square distribution with 1 degree of freedom. Okay. So if there is no population structure, since the vast majority of the SNPs are not going to be associated with our trait of interest, we expect that the vast majority of them should behave like the null under the null distribution. Okay. So this is what, for example, we might expect the distribution of it to be something like this. Let's say this is a chi-square 1. That's the distribution that we would expect under the null hypothesis. All right. So this is So this is what we expect under the null. We expect that test statistic to follow a chi-squared 1 under the null. There's no association. All right. So you test all your SNPs. You plot your histogram, for example, and you expect it to follow something like this. If there is population structure, the statistic will deviate from a constant distribution. So this is what we expect. We expect it to fall like this. But let's say in reality, we have something that looks like this. Somehow it's shifted. All right? So this is what our data actually looks like. So this is what it looks like, and then I'll just do a dotted line for. This is what our data actually looks like, but we expect it to look like this. So it's shifted, right? Because if there is population structure, then you have inflated test statistics. You have larger values than you would expect. Larger values lead to false positives if there's not a true association. But the vast majority of SNPs are not going to be associated with your trig. Okay? So essentially, the idea behind genomic control is you use the genome to control inflation. This somewhat tells you how inflated, because this is what we expect if there's no inflation. This is what we observe. The difference in these two distributions tells us about inflation. So we're using the genome to control inflation. We're using the genome first to estimate inflation, and then once we determine how inflated the test statistics are, then we can adjust for it. Okay. And so that's what we do here. So we take the median of our data, of our test statistic, true data, and we compare it to the median of what we expect under the null hypothesis. So genomic control says, give me the median of what I would expect, for example, maybe something around here. If it's chi-squared 1, the median of chi-squared 1 is 0.456. Okay. And then we look at the median of our test statistic, well, maybe somewhere up here, of all our data, and we use that ratio to get our genomic control inflation factor. So why are we using the median? Why are we using the mean of our observed test statistic?
It's not prone to huge outliers.
Exactly. So you may have a few highly significant p-values. I mean, where your test is large, and it'll bring the mean way out here. Okay. So you don't want it to be influenced by a few highly significant markers. You want the average, the middle of the distribution, okay, to kind of guide how inflated you are. Any questions about that? So the genomic control inflation factor, it sees what the lambda is based upon this distribution, but they use the median to determine the inflation. And then you just correct it. So all your statistics are inflated by a factor of lambda. So we just take our rich statistics and we just divide it by our inflation factor. So that is, has anybody heard of genomic control? That's genomic control inflation factor. That's what it is. So we're just using the genome to control for inflation due to population structure, due to violations of the assumption that. So what's violated? What's violated in the Armitage trend test? What is the violation? What's violated? Here's the Chi-square test. What's being violated? Independence of what? So the sample individuals are not independent. Okay. So under the null hypothesis, the assumption is that if there's nothing going on, there should be no association between your SNP and your outcome. But in this case, under the null, there is an association, right? Because of confounding due to ancestry. And so this was an approach, this was one of the first approaches to try to correct for population stratification in genome-wide association studies. Just like principal components analysis is the most popular approach to infer genetic ancestry, it's also the most popular approach to correct for. I heard a couple people ask me about Eigenstrahl. Let's talk about the Eigenstrahl method. So you know how to do PCA now. You have data on individuals across the genome. You construct a genetic relationship matrix. Okay? So essentially, at each SNP, a low frequency, and here I'm using the location X to be the number of copies of the reference of the SNP. You just, for all possible pairs, you get an average correlation. So you have your matrix. You perform PCA on that matrix to get your top eigenvectors, which you did in the last lab. You got principal components and you plotted them. So the Eigenstrahl method is, now we're using the principal components. Before, when we did PCA, we didn't use any phenotype data, right? We just looked at the genetic data and just looked at if there's any clustering among individuals and plotting it and seeing if there's any grouping and any differences among individuals that can be explained by the top PCs. The Eigenstrahl method is actually quite simple. It's similar to linear regression, except that now we include principal components as covariates in the model. Why are we including PCs? To correct for population structure, right? So we're adjusting for any differences in the phenotype that can be explained by ancestry. Does that make sense? By including principal components in the model, if indeed these PCs are reflecting ancestry, by including the model, we say we're testing for association with a genetic marker, but we say, is there any association between outcome and genotype beyond what can be explained by ancestry? So we're correcting for ancestry differences among individuals. So if individuals who have high African ancestry are more likely to have higher cholesterol levels, then we adjust for that. So we're saying that, okay, those who have cholesterol levels that are high, for example, if you're African, that means we know you have high cholesterol levels. So of those that have high cholesterol levels because they have African ancestry, is there any additional information that tells us about cholesterol levels in this SNP beyond what can be explained by ancestry? So by including it in the model, we're adjusting out the effect of ancestry on the outcome. So this says, beyond what can be explained by ancestry, is there any additional predictive power on my outcome at this SNP? Does that make sense? So we include the principal components in the model to correct for population structure. So you guys know how to do linear regression, you know how to add covariates. So one thing you can easily do if you're using Plink is you calculate the PCs, get a file, include PCs in a text file, and then in Plink you run your association analysis and just add the top components as covariates. That's Eigenstrahl. Doesn't matter if you get the Eigenstrahl, if you get the PCs from the Eigenstrahl software or do it yourself from SNP Relate, it's going to be the same. It's just single value decomposition. They didn't invent that. It's been in a long time ago. So it's going to be the same no matter what. There may be small tweaks as far as minor low frequency cutoffs that you're going to be using, but it's going to be almost the exact same. Right. So that's the Eigenstrahl method. Okay. So you're still testing for association with the SNP, but you're including these extra principal components that are reflective of ancestry to control for confounding due to ancestry on your trait. So that's by far the most popular approach. Now, the Eigenstrahl method was developed for unrelated samples with population structure. Okay, so in samples with related individuals, all right, this approach won't work well. All right, so Eigenstrahl works well in determining differences in ancestry if individuals are unrelated. But if you have related individuals in your sample, what do you think is going to happen with the principal components? So it's a genetic similarity matrix. If I have parents and offspring in there, they're going to start clustering even tighter, right? Because if you think about it, population structure is relatedness, but it's just distant relatedness. They share distant ancestry. But if you throw recent relatedness in there, pedigree, siblings, first cousins, okay, that's genetic similarity too. But their correlation is going to be higher than ancestry correlation. Okay? And so if you look at the top principal components, if you have related individuals in there, the top principal components could be reflecting pedigree structure, family relatedness. Those individuals are going to cluster. And it's not going to represent ancestry difference. It's going to represent recent ancestry, pedigree, familial relatedness. So this is a concern, particularly in samples where you have incomplete or misspecified relatedness among sample individuals. So here's an example where we sample these individuals. We have some information about pedigree. So here we have one pedigree that has 2 parents and 2 offspring. Here we got 2 parents and 1 offspring. But genealogical information may be missing. So here, for example, there's the genealogical individuals, part of this information, genealogical information is not available. That connects these 2 individuals, these 2 families. Okay? So these 2 individuals are actually related, but if we model the individuals as if they're unrelated, okay, then that also can lead to spurious association. Okay, so you can also get false positive by not taking into account that individuals are not independent. Okay, there's some correlation among individuals. That goes back to population structure. Population structure is correlation among individuals. They're correlated genotypes. They share a distant ancestor or many distant ancestors. That's why they have similar genotypes. Okay? If we're talking about individuals who share a recent ancestor, then you have pedigree. So that's also structure that if you don't account for it, you can get spurious association. Okay. So someone asked a question about what do you do with cryptic. I think you asked this question, right? What's your name? Yeah, so this is for you. So this is for the cryptic relatedness among individuals. Okay, so linear mixed models have been demonstrated to be a nice approach to handling samples with both cryptic relatedness and population structure. Okay, so the idea behind linear mixed models is as follows. So we have some outcome Y, trait Y we're interested in. Okay. We have some covariates that we're going to adjust for. Okay. Then we have some genotype that we're testing for association. So this is what we want to know, whether or not our genotype is associated with our trait. Okay. But we have 2 extra components. So we have what we call, so the standard linear model just does this. It just, you have your covariates, you're testing for your genotype. So this gamma, we're testing whether or not that's 0 is an association parameter. If gamma is equal to 0, then there's no association. And then it's error term. But we add this extra random point, and it goes back to the models I was telling you about yesterday, where this is the genetic component that may be influencing the trait. Some people are going to have a G value that increases their trait value. Some are going to have a G value that decreases their trait value. Okay. So these are the fixed effects of the model. Fixed effects are age, sex. This is the matrix of fixed effects in the intercept. Beta is the vector of covariate effects. We don't really care about that. We just want to control for age, sex, information that may be influencing our trait. We're interested in association between this. This could be a beta, just some parameter, association parameter that under no hypothesis should be 0. So these are the fixed effects. So why is it called mixed effects model? These are fixed in the analysis. We measured this. Okay, so that's fixed. Now there's random effects. So these are the random effects. G, this is the background polygenic effects that influencing the trait of interest. So G is all the different genes and genetic variants that are influencing the trait that we don't know about. Okay? And then E is just the random noise. Okay? So G is a vector of polygen effects. Okay? We assume it falls normally with mean 0 and sigma squared G times some matrix, genetic relationship matrix. Okay? So this represents added genetic variants, and the psi matrix here is a matrix of pairwise genetic variants. So this is actually the same matrix that we perform our PCA on. But it's different than PCA. PCA is the top principal components. For the linear mixed model, it uses the entire matrix. So what we're saying here is that G falls enormously to mean 0, but we model the correlation among individuals. So we explicitly model genetic differences among individuals here, which is different than PCs. For principal components analysis, okay, remember the PCs are fixed effects. Okay, so fixed effects. So we assume that after we adjust for ancestry differences among individuals, that the outcomes are uncorrelated. Okay. If you have related individuals, this doesn't hold. If you adjust for ancestry, the outcomes are going to be correlated among relatives, right? So if I adjust, so if I have like siblings in a model, right, and I adjust for the ancestry siblings, and we're talking about, for example, BMI, right? Clearly, BMI values among siblings aren't going to be correlated, even if you adjust for their ancestry. So this is the problem with Eigenstraat if you have samples with related individuals. So linear mixed models are a nice approach because it explicitly models the correlation of the phenotype, and it says there's a genetic component, okay, and there's an environmental component, and so it measures the variance of our phenotype that can be explained by the shared genetic data among individuals. So it explicitly models the correlation among individuals. So any questions about that? Okay. So this matrix, as I mentioned, is the exact same matrix that's typically used with PCA, except that we don't just get the top 2 principal components, we use the entire matrix, we use all of the data. Instead of just including the top 2 principal components, the top 3 or top 4, we use all the data and we don't decompose the matrix. So Kangadol proposed the EMMAX linear mixed model method, and it's the same matrix. Okay. But now this matrix captures both population structure and pedigree relationships. Okay. They're all just measured correlation, but people who are related are going to have a higher correlation than people who are unrelated, quote unquote, are unrelated but have similar ancestry. Okay. So typically you're going to estimate it using a large number of markers. You probably need about 100,000 typically to capture fine scale structure. Okay. And so the idea is actually simple. So for genetic association, the EMMAX mixed model approach considers this model. Okay. And then we have the variance components are then estimated, right? So essentially what we say is this. So we're trying to model the variance of the phenotype. So in the simple linear regression model, for example, if Y, we assume that this is simple linear regression. So Y is an identity matrix. So we assume that all the individuals are independent after you condition on phenotype. Okay. The linear mixed model does the following. It says no. I'm going to say the variance of Y is going to be equal to sigma squared G times the matrix plus sigma squared E times the identity. Okay. So this is saying I'm modeling the variance of individuals based upon how much of the genome they share. Okay, so the idea is individuals who share more of the genome, identical, should have phenotype values that are more correlated, right? Which is expected, right? If the trait is indeed genetic, if you're MZ twins, then you should have a much higher correlation of your phenotype than an individual has with a first cousin, right? So that's the whole idea behind heritability. Individuals who are more closely related should have similar characteristics. Individuals who are more distantly related are going to have less characteristics in common. Okay, so that's the idea behind this. We're trying to say, okay, we're not assuming that individuals are independent. Those individuals who share a lot of the genome identical, and how is that measured? Through correlation. Those who have genotypes that are more correlated, okay, you expect their variants, you expect them to have more similarity. So this models the variance of that. So we take into account that individuals who have similar genotypes should have similar phenotypes. Individuals who have less similar genotypes should have less similar phenotypes. So we explicitly model the genetic relatedness or the correlation structure in that way. So we have to get estimates of that. Okay. So originally, when this was first proposed, it was difficult to do this on a genome-wide basis. It was difficult to estimate these parameters on a genome-wide basis because it took a long time. It wasn't feasible to do this in GWAS with 200,000 SNPs. For linear regression, you can do it fast. It's closed form solution, fast, as you saw on your computer. It's very difficult to do this. And then the EMMAX approach found a way to do this in a fast and efficient manner. Okay? And so we estimate the variance components using mathematics. So we assume like multivariate normality, and then you estimate these parameters, the variance component, based upon maximize the estimation. So interpret this. So sigma squared G starting from that right over the variance of Y. What is that?
So that be the fraction explained by population structure versus the total variation?
Or the not necessarily structure or so this represents the portion of variance that can be explained by the genetic factors.
Okay.
So what is this?
So that's just the
heritability. So essentially it's a heritability. So this is how people are getting estimates of heritability using linear-based models. So they're getting estimates of this, and they try to restrict the sample so that it doesn't include really close related individuals, but they estimate heritability of a trait based upon this. Okay. So this is sigma squared G. So the total variance here is sigma squared G plus sigma squared E. That's the variance of Y. Sigma squared G. So this is the portion of the variance that can be explained by genetics, right? Because this matrix is all genetics. How do we create this matrix? Genotype data, right? So we're looking at what portion of the variance can be explained by correlated genotype. So this only was based upon genetic data, no phenotype. Right? So this measures the proportion of variance that can be explained by genetic data. So that's how heritability was originally calculated, using families, right? Because we assume that people who are closely related to each other are going to have higher correlated phenotypes, more distantly related are going to have less correlated phenotypes, and then they were estimated in this way. But it turns out your sample is large enough, you can actually do this in population studies as well, where people are distantly related, right? Because at the end of the day, we're all related. We all share some kind of common history. So some individuals, even though they're distantly related, those individuals who share a little more of the genome identical have a slightly more correlated outcomes than others. And if you have a sample size large enough, you can get unbiased estimates of heritability. Quick question. So Peter Fisher and others have published some work on estimating this, and that was kind of like motivation behind the missing heritability. And so Peter Fisher was showing that, hey, the missing heritability is there because when we estimate this, our variance components in the GWAS, we get pretty high values for this. And so that was the idea of like, well, it's there, we just need to increase our sample size. So Peter Fisher and colleagues, they proposed, if you're trying to estimate heritability of a trait using this type of model, they wanted to restrict the sample to only those individuals who were distantly related. Any thoughts on why? So this model assumes, for example, that for individual yi and yj, right, that the variance is due to the variance of these two values, individual yi and j, is equal to variance due to genetic factors times some like kinship, how closely they're related to each other, or I'll just say omega ij, plus some unique environment. So this is what this is saying. For individual I and j, now I and j, this is how it's modeling the covariance of I and j. Okay, so this is what it's saying. It's saying covariance for y and yj is sigma squared g times how correlated their genotype are, genome y, plus some unique error term. Okay. But if we assume that the errors, that the environment is independent, then this should be times 0 if we assume independence. If I and j are related, can we assume that, so this is, for example, is the covariance for EI, EJ, the error term environment, EI, EJ. So if I and j are unrelated, then it might be reasonable to assume that this is 0, right? But what if I and j are related to each other?
You could get the environment.
Environment. The shared environment can have a huge impact on the correlation of the covariance of the trait, right? So how much, forget genetics. So we're actually doing a study now. If you look at individuals who are unrelated and live in the same household, their phenotypes are correlated. Their height and weight are correlated, right? People live in the same household, what are they doing? Even they're unrelated. This is correlated. The environment is correlated. There's not random mating, right? You mate based upon people who have maybe similar lifestyles as you. Okay? So imagine if you have both your relatedness as well. So there's a huge component, that shared environment, that can mess up this calculation of heritability. And that's why it's been argued that these heritability estimates that are based on families, pedigrees, are incorrect because it doesn't take into account shared environment. It's only based upon sigma squared g over sigma squared g, sigma squared e. Well, what about the shared environment? All right? That's nowhere in here. And so some have argued that the missing heritability, the distance between what we see in our genetic association studies and the variants that we identified, and the heritability estimates from pedigree, is a huge divide. But is it due to overestimation of this? Because really, it should be sigma squared g plus sigma squared e plus sigma squared some shared family environment. Okay? If you remove that, you have overestimates inheritability. If you include this, then that would be a better estimate of inheritability. So there's a sheer family effect. So to get around that, Peter Visser's group, where they said, okay, we're going to exclude individuals who are related, only include individuals who are related no more than first cousins once removed. So why that? Think about that for a second. They only include individuals who are no more related than first cousins once removed. I heard something. Yeah, you remove the household effect. Who lives with their first cousin once removed? Not you. Right. So you get rid of that, the shared household effect. So, in any case, they model this, they use an estimated genetic relationship matrix, estimated from the genome. And then they just do an association test where the score statistic is tested under the hypothesis, but now you're modeling the variance of the phenotype, taking into account the correlation among individuals, the relationship among individuals. Okay. So that's the EMMAX. So Gemma, Matthew Stevens, they published a paper in 2012 in Nature Genetics where they did the same thing, but they estimate new variance components at each SNP. Okay, so for each SNP, they estimated a new heritability estimate for each SNP. Okay. So if you look in the past few years, there have been tons of Nature Genetics papers on this, and to me, they've all been doing almost the same thing, just minor tweaks here and there to try to get speed up of these methods. But there were tons. There was a paper last year about Alke's price and all where they did. It's a recent paper this year. So their linear mixed models has quickly become the method of choice for doing association testing in samples with structure. Okay. So what about for dichotomous phenotypes? So this was part of my dissertation thesis. We wrote a paper in 2010 on how to do this if you have case control. So here, the assumption here is that Y is quantitative, right? Y follows a normal distribution. So if you have dichotomous traits, you could do something similar. We're using empirical covariance matrix, so you can capture correlation structure among individuals if you don't know the pedigree, and essentially allows for valid association with case control designs and samples with population structure. So, and there's a number of ways to extend Pearson chi-square test, Armitage's trend tests using this, and essentially we just appropriately incorporate this covariance matrix to account for the correlated genotypes among sample individuals. Okay, so here are some of the references for this. All right. So we have a little bit of time left. I wanted to talk a little bit about this package. So to how to do GWAS NR using linear mixed models. And so so there's a homework example, not homework example, it's optional, where you can try to do this in R. So look on the back side of the sheet that I gave you. And so you're going to use the Genable package. If you don't know about Genable, which most likely you don't, you can question mark Genable, look at the vignettes. So Genable takes a Plink file, but you're going to have to do a transped Plink file for this, and so you can analyze both the height and the transfer and phenotype. But now we're going to use a linear mixed model where we don't assume that the individuals are unrelated. We don't assume there's no population structure. We're going to capture the structure using the genetic relationship matrix. And so I have R code there for you that you can use. warning, okay, it's very computational intensive, okay, so you may not finish it here. It might run for a long time. So so what would be computationally intensive? Let's think about it. Okay. Okay. So think of the model. Okay. So what's going to be computationally intensive here? The computer relationship matrix. So if you have 4,000 individuals and you have 250,000 SNPs, and you got to, what's 4,000 choose 2? You got to get all possible pairs. Okay. So what is that? How many pairs are we doing? Let me pull this up real quick. How many people, let's say it's 4,000, I can't remember. 4,000 choose 2. Okay, that's a lot of pairs. So that's 7,998,000 pairs that you're going to have to calculate correlation. Plus, you got to get an individual's correlation with himself. So add 4,000 to that. Okay, so that takes a long time. So if you start this, your computer might freeze up. It's working, but it might freeze up. I don't think it's going to finish in time unless you have a pretty fast computer. I think it took mine a couple hours. So that's it. That's just a warning. You don't have to. You don't have to do it if you're worried about it freezing up. I did it. It took a long time, and then I saved the files. So I'm just going to read in the files that I have, but it may take you longer to do it. Okay, but you can still look over the code. You can still get the transpose ped, and then in about 20 minutes I'll share the solutions. And also. Is there supposed to be a tutorial section today? Is that right? Okay. Did you know about that, Mike?
No, those people.
Okay. Oh, no one knew about that? I don't know. Is there a tutorial session? Someone said yes.
What is it? Session?
Yeah, so basically from 5 to 6, like if individuals have questions or anything, I know you have to go, Mike, I'll be here, that we can go over any questions or anything that you may have, or the discussion. It's kind of up to us. So I'll be around if anybody's having problems or questions with some of the material we can discuss. Okay? All right. let's take a simple example like this. Let's say Y1, the variance of Y1 is 2, the variance of Y2 is also 2, right? And the covariance of Y1 and Y2 is 5 what's the variance of Y2? In reality, what is it's not it's 6, right?
Well, I mean, that's
2, yeah. So if you follow this as you're underestimating the variance. So if you don't, so if that's the only yeah, yeah. So if you don't do it, it's underestimated. It just tells everything else is about shared
So you basically just estimate the population.
No, so from there, we take the slips and plot them the same. And then from there, the same thing.
So you do exactly that.
Exactly. You can do it with sequencing data or GWAS data.
So what you do if you had like people that you knew they were kind of related from that?
Yeah. I don't think you could really but with the phenotype and the fact that it's being Down syndrome, it's very unlikely that A, related individuals are going to have two kids with Down syndrome, and B, that there's two kids with Down syndrome who both have birth. So it's like, you know, each level you go up, there's less of a chance that you'll get relatedness. So I guess it depends on the context of the question, whether that would be very complicated. If it was diabetes, then yes.
Your headache is over for the summer, or are you doing any other?
You could.
We got
Oh, that's right. But hopefully for that we can use. It's the same time period.
yeah, exactly.
Okay. Yeah, I might clean up some of my slides a little bit further, but otherwise,
So you kind of straight away back.
yeah, that'll be an interesting one.
Yeah, I think so.
You been to Taiwan before?
Never been. Is it what's the market like right now?
Market?
For as far as like the is it to the dollar? I don't know what do they
Oh,
use?
things are definitely cheaper there. Is the
okay.
perception? I mean,
Gotcha. Okay.
you know, it's yeah.
Okay. Well, that's good.
Yeah, things relatively cheaper. I mean, it's not like a cheap place, but it's not like going to China mainland. But
Oh,
it's
okay.
definitely- Yeah, yeah, and Taipei is a modern city. It's not like you go
okay.
to the boonies or anywhere.
I guess it depends on what your session is.
Yeah.
Are you trying to relate this?
I need to figure out if they're going to send somebody to pick us up at the airport, or
Yeah,
if I'll ask them. If not, I'll arrange for transportation for us because we're on the same flights, right?
I'm assuming that they're gonna arrange all that. I'm
If
hoping.
not, I will just deal with
Okay.
it. I mean, it's like, yeah.
Yeah, I'm hoping they're gonna take care of that.
I don't know. I've been there for a few conferences, and it's like a couple of conferences, and it's always irritating.
Oh, really?
Hopefully, the weather's good. It's probably gonna be hot, but
Yeah, it is gonna be hot that time of year. That's
Yeah.
right.
sorry about this tutorial thing. I just pulled
Yeah,
up the yellow sheet, and there's something. Is this like normal?
Yeah, they typically do. I forgot to tell you about it, but it's not a big deal. It's just like folks who want to ask questions or want to discuss anything. Yeah, so it's not a big deal at all.
Yeah, I'm sorry, I just didn't realize it.
Oh yeah,
like,
not a big deal at all, man. Not a big deal at all.
Yeah, I'm not good at reading emails. If it's longer than like a screen, I just forget it.
He's like,
So
okay.
it's possible that they sent it to me. I just am bad at that.
My guess is they didn't. Yeah.
Nobody ever actually sent me the website for SISG either. So I was looking for it the other day, and I was like,
Listen, my guess is they didn't send it. I mean, this
it's a little bit.
disorganized and
Yeah.
so.
Yeah. Well, I mean, there's so many of these things going on at the same time.
Yeah. Yeah. So no worries. Like I said, I'm gonna stay a little bit. I can't stay too long either. Just just answer the question.
Yeah, and if not, I can field questions tomorrow at lunch.
Yeah. No problem. Yeah.
And I know realistically for the last session, I'm not sure that I'll have much software demo.
Oh,
that
okay.
one, I may just have more discussion.
Yeah. That's perfect. Yeah. That's perfect.
Okay.
Let me see.
Tomorrow I can take care of everything. So.
Okay. Yep. Sounds good. See you
Email.
now. Yep.
Yeah, I'll probably head out.
Yeah.
Yeah. Tomorrow my wife will take care of child duties.
Yeah, no, that's tough. So where?
Where is Queen Anne? It's where I have to go for. So it's near the Hutch, but it's like fighting traffic to get down there.
Oh yeah.
It's just irritating.
Yeah.
Awesome. Thanks a lot.
Yeah, sure. So I'll see you tomorrow then.
Yeah.
And if you want me to post anything, just shoot me an email and I'll do it.
Yeah, for the most part, I think I'm just gonna copy up a bunch of jump drives and just have like 4 directories in there, one for each lecture.
Okay. Yep. That's perfect. Sounds great.
Right.
Yeah.
Thanks.
All right. See you. Has anybody tried to run the GRM yet?
like when you have repeated measurements?
Yeah, you can do that. You can do that too.
Okay,
Yeah, that's right.
there's no repeated measurements in our case, right?
No, but it's basically for correlated data.
Okay.
So when we say repeated measurements, that means you have multiple measurements on the same individual, so those measurements are correlated.
Okay.
Just like our measurements are correlated because people are related to each other. So it's just correlated data.
So it's
Yeah.
more general than just repeated measurements.
Yeah, for sure.
Okay.
Just correlated data. So you try
Okay.
to model the various components that could be due to shared environment, shared or repeated data, right? So there's some correlation structure you have to impose on the correlation of multiple observations of the same individual over time. Yeah.
Okay.
Yeah. So there's a lot of applications.
Cool, thanks.
Okay. Okay. All right, so let's take a look at some of this. Okay. So for this analysis, you first needed to create a TPED file. So that's a transposed PED file. So did anyone do that? I know it takes a long time. And how big is that file? It's got to be huge, right? Because now it's no longer compressed, right? So can anybody do it? Did it finish or still doing it? 5 gigs? Okay, delete it when you're ready. But that just gives you an idea of how big these files can get. So there's 5 gigs. But when we use the bed file, it's like 200 and how many? I forgot how many. 300, megabytes versus 5 gigabytes. So it's a huge difference. All right. So you only really need to do that once. It's unfortunate that this package makes you do a TPET file. The other packages, like the SNP Relate, it takes the bed file, so you don't have to create. So you reduce it now. So unfortunately for this one, you got a bed file, but then you got to create a large text file in order to use it. So, but anyways, you're gonna read the data and then install Genable in the library as well, and then library to load it into your session. And this convert.snip.tped, it basically creates an object that can be used by the software package. Okay, so I create so it's gonna take the TPED file, the TPED file, and then it's going to get it output a raw file. So you can get some basic information on transferrin, but you guys have already done that in your previous analysis. And then what I did here is I created a phenotype file that I'm going to attach to my transferrin object. So based to my transfer object. So basically, what I do is I create a file with individual ID, sex, transferrin, height. These are my 2 phenotypes, and then essentially I load it to it, and then I essentially attach it to this genotype data set. So this the phenotype information, transferrin, height, dash that I created, and so this creates a new object that contains both the phenotype information and the huge genotype data file. But now this .raw file is kind of small. So once you create this .raw file, you can get rid. You can delete the TPET file that is taking so much memory on your computer. Okay, because now this is all it's going to need to do the analysis. All right. Now, what takes a long time is the GRM. So I can't remember how long it took me to create the GRM, but but one thing in R, once you create something like this, you want to save it, so you don't have to read in the TPET. So that's why I have the save transfer.gr. So this is the file you read in without having to recreate the object. So this contains all the information you need on genotype and phenotype. So you want to save this file because it's in R data format. So now when you read it in, it's much smaller. It contains all the information that was in the TPET file, but now it's in a compressed form. All right, so you want to save that. Similarly, I created a genetic relationship matrix here, and then I saved that as well. Okay, so I've saved those 2 objects, and so now I read them in. So to read it in, once you save something. Once you save it, then you can comment this out, and then you can just load it from now on. So next time you use this data set, just load that. You don't even have to do anything else. Because the data, all your data is here. You have the genotype phenotype information in this file, and you have the genetic relationship matrix here. Okay? So now that's all I need. I'm ready to go. Okay. So the first step is it calculates the variance component. So it calculates sigma squared G and sigma squared E. All right. So it takes a little bit of a while, but for the if you want to estimate heritability for transferrin, for example, what an estimate is the heritability is around 50%. So this is this ratio. Okay. For height. You can look at the help files to figure out how to what would this mean, but this is the estimate of the heritability for height. So for height, it's around 77%, which is consistent with heritability estimates for height. Okay. Now let's perform the linear mixed model. So their method is called the gamma method, but essentially just doing linear mixed model. And so we give it the variance components estimate and transferrin.gr, and then we just run it. So how does it know which phenotype we're using? From that information isn't here in this H2A when we estimate variance components. So now let's just run the GWAS using linear mixed models. So it might take a little while. It did something. Okay, so it's done. So I have my results. So now I just want to look at, so the results are saved. I saved it as gamma.transferrin. So let's look at the rows. Add my row. Okay, so these are the rows of the SNP names, and then this is a way to pull out. So let me see. Let's just look at the first. There's head, GR. Okay. So the results are as follows. They give you the SNP, the chromosome, the position, the strand, the number of individuals, the betas, standard errors, the chi-square test, and then here, for example, would be the p-value, if I'm mistaken. Okay. So similar to the Plink, but now we're doing a linear mixed model to account for relatedness among individuals using a genetic relationship matrix. Okay. So I'm just going to extract the columns that I need for my plots. Okay. So add my data 2. So this is what it looks like. So I have all the p-values. This is my p-value for one freedom test. And so now we can just use all the GWAS tools, functions that we use for the Plink analysis. We can get some plots. Okay. So we wanted to look at our top SNP, for example. First, so our top SNP has a p-value of 9 times e to the minus 36. Okay, so slightly smaller than I think the one from the Plink analysis. But like I said, the Plink analysis didn't count for relatedness among the individuals. And you saw some inflation even with the height phenotype. Okay, so this is a more appropriate analysis because there is some relatives in that sample that aren't accounted for when we do simple linear regression with the Plink. So we can do a Manhattan plot as before. Okay, so pretty similar. Okay, so that's one of the software tools available. You can also do a QQ plot since you have such strong significance. You see, but for the most part, it's doing a pretty good job of controlling for inflation. And what are these points right here? These are the significant points. Okay, so you want the vast majority of the points to kind of fit on this line, and then if there are some significant points, you do expect some deviation, but the vast majority of the points should fall on your business line if the test statistic is well calibrated. Okay. So any questions on that? So this is just one of the software tools available for linear mixed models. There are a number of other software tools. So all the papers that I mentioned in the lecture, they have their own software tools. Most of them are in Unix or Linux, but you can easily run it on your machines as well. But this is one of the only ones that I know of that you can do it in R, which is why I chose to demo it. Okay. So if there are any other questions, we can stop here. So I'll stick around for half an hour. We can answer any questions, and if you want to stick around, feel free to. If not, we'll see you tomorrow. I'll post the. I'll post. Well, you guys have everything. I didn't change anything, so I don't have to post anything. You guys have all the commands. So, but I think I'll post our solutions for the Plink session from this morning as well. But everything else, I didn't make any changes to. All right. Thanks.